So as she said, I work on the Curiosity Rover. So this was actually my second summer. I just got back from Los Alamos this Wednesday, actually, and I worked through the whole summer. So this was our ChemCam group for 2016. So there's not many who actually work on this specific instrument. They said, at least in 2016, we were the only 3 students actually working on it. Everyone else was graduate students, postdocs, etc. But for undergraduates, we were the only 3. And these are one of the only pictures that exist of me on lab property. So you can't take pictures on lab property without special permission. So they had special permission this one time to get pictures of us. And then they used it on Instagram for publicity. Sounds like a national lab. So a little bit about Mars. Today is actually Sol 1791 for the Curiosity rover. Sol is what we say for Mars days. So Mars days is 24 hours and 40 minutes. So you can't just call it a day because you get really confused of, do you mean Earth Day, do you mean Mars Day, what day are we actually on? So we give it a whole other day and just call it Sol. So I've been working up, so my last research project was actually from 1650 to 1750. So pretty recent data. And part of the thing there is I always just keep downloading the newest data and analyzing it to see what's in it each time. I'm one of the first people who actually ever see some of this data because a lot of people are still on operations or they're writing papers. They don't have time to just be a student and just sit there day after day downloading the newest data. So this is Gale Crater. This is where our rover landed. The yellow circle is actually where our ellipse landing was, so we had to land in there. That was the best projected area for us to land. We chose this because there was geological signs water used to be present there. The whole idea of this rover was to see and look for signs that Mars was at one point habitable or potentially habitable now. So we wanted to find something that had water because water is one of the first indicators of habitability. So this is the Curiosity rover in artist description. So since Curiosity's primary scientific goal is to explore Mars, they needed a payload of instruments that could do this. So they looked for biological potential, they looked for geological, they looked for water, weather, radiation, everything. And the radiation levels was specifically used to see if we could put humans on Mars and how safe they will actually be. There's still great data coming from it, but that's not used a lot for just right now. So I work on ChemCam. It's this instrument, and I have another one. So this is all of the rovers we've put on Mars. So Sojourner, that's our smallest one. It lasted only 90 sols. And that was actually a lot. They thought it was going to last a week, or that was its primary goal. They let it go for 90 days, Mars days. Then the Mir twins, which Todd worked on, Spirit and Opportunity. Opportunity is still running. And then the last one is Curiosity. And something that was really interesting to me that I heard was anyone under the age of 20, there's always been a Mars mission going on and working, whether it was just a satellite or a rover. So everyone under the age of 20 has always been having Mars data come down for them and being accessible to them. So actually, I would like everyone to look how big that rover is and look how small that one is. We really amped it up for the Curiosity rover. It was much bigger. And one of the things they were really excited about is they could use so much more data and payload instruments, but also if they want to put humans on Mars, that's not going to be easy. That's not going to be light. So by putting nearly 2,000-pound rover on Mars successfully without just crashing into the surface was an engineering accomplishment. And that stands 2.2 meters or 7.2 feet. That's pretty tall. So that'd be roughly about my height with the stage and heels. That's how tall this rover's standing all over everyone. So that is a replica of the wheel. That's how big it is, from about my kneecaps to my hip. That's a big wheel. And I made sure to get these little dots in there. Anyone know what they're for? I bet Todd does. Okay, so now the way they explained to me, they're like, oh, it's for engineering purposes. If you get a rock in there, in the wheel, you don't want it just rolling around, so the holes let the rock be free. What they mean is they wanted to sneak JPL's logo onto there. That is JPL in Morse code. It does let rocks out of the wheel, but they wanted to write JPL. And that is actually the rover on Mars. It does, in fact, write JPL. This is the video, I think. So we've launched from Earth. This is the rover. Not that you can see it right now because it's encased. So we're speeding up. And we begin the 7 minutes of terror because they could not use parachutes for a rover this heavy. So they had to come up with more engineering ideas. So what did they do? When they're plummeting through the atmosphere at very fast speed, they use a parachute for the beginning. But then they drop it and they use retro rockets. But you can't really put it that close to the surface unless you use a crane. They literally used retro rockets to gently push the rover on the surface. Then they had to cut the cords and send it flying off because you don't want that falling on your rover. That's really bad. And here's Curiosity's perspective of the whole thing. The heat shield's being kicked off. The black lines you can see, that's dunes. You can see all this dust being kicked up. Keep in mind, they weren't seeing this live. They got the signal that it went through the atmosphere about 7 minutes before it did. By the time it landed, there was about a 7-minute gap between the Mars signal and Earth. They didn't know until about 7 minutes later that it had in fact succeeded. So they got all of this once it had already landed. And you might see better on these screens, those small little lines. But they succeeded, in fact. It was an amazing engineering accomplishment that they've now learned that they can do, and they will use and replicate for the next rover. So what did we see when we got there? We saw craters, we saw dust, we saw things that actually resembled things on Earth. All of these are in fact Mars pictures, but if you go to New Mexico, you can actually see things like this. We have dunes, we have rock formations like this, things that we've been seeing on Earth already, all of a sudden we see on Mars too. If we know the processes of Earth, then we can say what the processes on Mars are. And this shows a lot about what the environment of Mars could be. So this is one of my favorite pictures because it shows, this is actually an image from our ChemCam device, and then it shows things that we've been seeing on Earth. They're not that different. So same thing here. We've been seeing all this dust and dunes, and we actually have to be very careful about going through dust or sand like this. If the sand is too thick and our rover gets stuck, that's a problem. So we always have to test out how deep is the sand, how thick is the sand, would we get stuck? Because we need backup plans. We can't get stuck. So it kind of shows like us testing out the sand. This one we actually drove through. And this is Mount Sharp. This is the biggest and highest mountain in this crater. This was at the very center of it, and it's taller than Mount Kilimanjaro from the base of the crater. And this is more dunes in front of it. So this is a rover selfie. They're always fun to look at. But you notice, like, we didn't land something else with the rover, so how can a rover take a selfie of itself? If you notice, it's kind of curved on the edges pretty drastically. And yet, if you've seen pictures of the rover, you know something's missing that's supposed to be right here. It's something that you normally don't see in a selfie of yourself, unless you're bad at taking selfies. And that's your arm. We actually have a camera on the arm that takes rover selfies. So this is about 60 pictures mosaic together, and it just cuts out the arm. This is why you get pretty drastic things on the edge, and yet the rover is perfectly centered. So we actually landed in August 5th, 2012. That was 5 years ago. And yes, we did actually have a big celebration for it because that's 5 years of this rover still working. And that's pretty hard because there has been difficulties along the path. So what is ChemCam? So ChemCam is two things. It's chemistry and it's a camera. So the chemistry is a LIBS, which is a laser-induced breakdown spectroscopy. And then the camera is a remote microimager. So as you can see with this, it shoots lasers, and they're actually infrared, so you wouldn't be able to see them in real life. But we pick targets, it shoots the laser at it, and takes plasma, and it hits it. And this focused laser actually turns that solid material into plasma. As that plasma cools down, it releases photons or light particles. We have instruments on our machine that says what elements are in each rock. So you would see spectrum along these lines. So each peak represents a different type of element. So there's iron, magnesium, silicon. That's how we know what's in each rock. And then for measure, we use our camera to take a picture of where we shot, because not all rocks are the same. Some of them have veins in the middle. You want to know if you're hitting a vein, if you're hitting a dark spot, what are you actually hitting? So this is one of my favorite pictures. I haven't done much analysis into it, but this is a meteorite we hit. I was actually back in school when this happened, but my email was just blowing up completely because everyone on the team was commenting on what we just hit, because that's pretty cool meteorite. And those 9 little dots, you can kind of see, that's where our laser hit. So how far can our laser hit? We can hit about 20 feet away from our rover. So this is a dime. We can hit 9 dots on each dime from this distance away. That's pretty far. It's what made ChemCam one of the best instruments on the rover, is because anything on the arm can only be in range of the arm. But ChemCam can get 20 feet away in all directions. And it has a pretty small spot size, less than 1 millimeter, or, oh, I guess it's the next one. This is what the ChemCam looks like outside of its box. This is what we use in the lab to test our sample specifically. And this is what a rock looks like when you're shooting it. That little white dot is actually light and plasma that we were able to see and photograph. So we've been on it 5 years, and it's one of the most used instruments on there, probably behind the cameras, because you need cameras for everything you do. But we've done 2,000 sequences. That's 2,000 rocks and soil samples. That's how many different sampling locations, because each rock and soil has about 5 to 20 sampling locations. We've operated on 10 and that many sols, and today is 1781, I think I said. We've operated for more than half the mission, and our laser is about to roll over our 500,000 mark, and we've taken this many pictures of Mars. This is an incredible instrument that they've used over and over again, and it's used in times where you think you can't get another instrument to work out because it might be on the arm or it might take much time. ChemCam is one of the fastest ones being able to use besides the cameras, just because of everything that's already programmed in, and just with our range, we can use it fast. So this is kind of what it looks like if you were in your operations room. Our operations rooms actually use NavCam images, which would be black and white, but those aren't nearly as fun for demonstration. So you would get this down in the morning, and then you would decide where you want to hit. And everyone brings their own biases. I personally like darker targets because that's what I'm studying, but you can't always do that. You just have to choose what you think is the most scientifically valid. So sometimes you get little suggestions like maybe here, maybe here, maybe here, maybe here. But you can also choose that if you see something that wasn't saw before, you're like, actually, I want to hit this area. At least in the close-up visual, you can see it's kind of layered. You get to choose what rocks to hit when it's your turn for operations. And that's really cool because you get to be the one to say, I think this one's scientifically valid. I'm putting my line out and say this one. And then usually I personally didn't get to pick any targets, but I got to name them. That was pretty cool. So you have to pick from a list. But I personally would have picked this one and then this one because I'm looking at dark ones. But that's also why they have people on rotation, so you don't always just get a data sheet full of dark targets. You get a variation. So this is what I was looking for earlier. That is the size of a dime. That's why I threw the dimes. That's all our shots. This is a penny in this dark area. You can kind of see it better over on those screens. That's the size of our sampling location. It's not big. So I'm here to tell you about why ChemCam has worked so well. So ChemCam, these are the 4 main accomplishments that I personally see, but there's some of the most recent ones. So the high concentrations of manganese, this is my personal study area. So manganese was theorized not to be on Mars in high concentrations. They knew the element was there, they thought it was going to be pretty low. Well, it was found at high concentrations. That kind of put a wrench in a lot of people's predictions and models of Mars because it just wasn't supposed to be there. So why does that even matter? Because manganese concentrates only with liquid water and strongly oxidizing condition. So we're in Gale Crater. We had the geological signs that water used to be present. So the liquid water part, you can just kind of mark that off. That one didn't surprise us. But this one, the strongly oxidizing conditions, what does that actually mean? Well, the theory right now is that there was more oxygen in the atmosphere than previously thought. And that really does mess with the whole theory of the Mars atmosphere climate model. Because if there was more oxygen, that means it was more Earth-like, and there's other things that could mean. So that's why manganese is so important to me. And when it's concentrated like this, it shows different things. So this is actually rock varnish, and that was just concentrated manganese. So as we shot into this rock, we could see the depth change of manganese. It was highly concentrated at the top, but not so much on the bottom. And we know that this little dark area formed after the rest of the rock. So it really shows what we can tell with the different Mars atmosphere and environment of this area. So the next thing is boron. So boron had never actually been found on Mars. They didn't necessarily think it didn't exist. It just had never been found. And we found it in a calcium sulfate vein. This means that there was groundwater later and came in and filled in that crack with calcium sulfate, and boron was also present inside. And its presence provides additional support that there was long-term habitability in Gale Crater. So not only did you just find high concentrations of manganese, you just found boron. And that was found a little bit later, but this is the example that they're showing right here. So as you can see, we've taken that many sample locations on this area. So we've done enough sampling locations that we realized that this wasn't an error, this wasn't a mistake, that's actually what we're seeing is this boron. Another thing was the silica halos. This just came out in a paper. So if you can see like these lighter areas around these fractures, it also shows the groundwater that came through after it, after all this rock had been deposited. This indicates that ancient Mars had liquid water for a long time, and longer than we originally imagined it could. And the last one, AEGIS. Definitely one of the most interesting ones. So AEGIS stands for Autonomous Exploration of Gathering and Increased Science. But what that means actually is anytime we do ChemCam, we get a picture down early in the morning that shows where our new environment is and where we're located with the rover, and we pick our targets. But after we do that, we drive. So like I said, we're not in real time with Mars. So we send the commands for it to drive, but then we just have to sit around until the next day to do operations again. We can't take any data at a new spot because you don't know what to hit, if it's safe, etc. Because if you use the arm, you might bump it into something and damage it. But with ChemCam being so tall, we've built in this system. We used to do blind targets, but you don't know what you're shooting. So you found something really cool, but where did it come from? That's what AEGIS does. And this shows roughly what AEGIS looks like and how we're training it. So this would be a new location that we just drove to. So there's no humans able to see this, but the rover has been trained that what is a good target and what is a bad target. The green ones would be what the rover suggests to shoot. Orange is secondary, blue has been removed, and red is a third option. So after it drives, we put in the commands to use AEGIS. So then AEGIS, once we get there, picks for itself. It decides what it's going to shoot, and then the next day we come back and we see what AEGIS chose. Did it choose good? Did it choose badly? How do we retrain it to choose better? So it's been interesting because it's been in function for about a year. I think they started really using it about July or August of last year. And I've done actually a lot of data with AEGIS. It's actually chosen, at least for my work, really good targets. So it has been becoming more useful, and we have increased our science because before we couldn't really do anything. We just would drive and stop. But now we drive, and AEGIS turns on, and it picks for us. So, summary, what we've done, we found high concentrations of manganese, we found boron, we found silica halos, and our AEGIS. That is part of this new technology that they've been trying to use for other things. ChemCam was just its beginning stage. They want to implement this across different technologies, but they had to do it somewhere where they could test it out repeatedly. And if AEGIS didn't work, you didn't just break the rover. And the idea is they want to put AEGIS on satellites or different probes so that if something was to happen that they couldn't relate back to the humans in time, it could navigate itself. So the ones I always heard was like Enceladus erupting, and if you wanted a probe by there, you don't want the probe going through that. You want it to circumvent and go around the erupting volcano. So that's what the beginning stages of that is. So we have gone this far, and that's only, I looked today, 10.66 miles over 5 years. It's not much, but we're heading towards this ridge, which has been a mission goal for a long time. That is hematite ridge. Hematite is an oxidized iron mineral, and we can tell from orbit that there's at least some amount of hematite in there. We're still not sure exactly how much. So the fact that we know iron oxidizes on Mars. Iron oxidizes much easier than manganese, though. So the fact that we've started seeing more manganese before this ridge can actually tell us a lot about this lake environment that we couldn't tell before, and it's actually turned into something very interesting. Still, we're not entirely sure, but we know something went on in this area. So for last, ChemCam got its successor on the next rover. The next rover does in fact look like Curiosity. They realized that the model works so well that they're making small updates and changing the payload around. But SuperCam was actually successful enough in its proposal to get on the next mission. What's become really interesting is that this one will only carry about 7 instruments that can do so many things, while Curiosity carried 11. And it's new because there's lots of instruments that have been on every single rover, but the only 2 that got successors on this one was ChemCam and then MassCam. So MassCam takes all the beautiful colored pictures, and it has a few other features that can do a lot of science with it. But those are the only 2 that got successors besides your obvious like navigational cameras and hazard cameras. So I'm really lucky because they're already talking about my future with SuperCam. And my specific work back at K-State, I use microbes to grow manganese oxides in jars. And then I take their spectrum to see what they're like. So right now, we can't use this for the Curiosity mission. We don't have the technology. But the next rover will. So the next rover will be looking for actual life on Mars. So right now, we're just trying to get your baseline sets because we want to know what does manganese oxide look like if it's biological versus chemical. So that's what we've been doing. And Todd kind of stole my idea, but this is Earth from Mars. And everyone you ever loved, everything, all your little problems that are just dumb, they all exist there. Because there is more out there than just your small problems.
I think we can both rip off of Carl saying.
Yeah, the little blue dot. So, okay.